for a few seconds. Okay, the lecture is being recorded from now onwards. In Monday's lecture, we started with this worked example in the Ithagini guidelines. Just to recap, we're looking at this particular set of guidelines, the Ithagini Design Manual. And we started with section 13 with the example that they have there. It's quite a comprehensive example and quite informative also in the way the design is done. Now, we looked at, in Monday's lecture, we looked at the drainage of area A, and we worked out the concentration time and the total flow arriving at point A. And then we also looked at the design of the pipeline from A to B. And, so to transmit that flow from the inlet at A to the manhole at B, and we stopped at that point over there. In today's lecture, we'll continue. What I want to do is get to the inlet at C and then the pipeline from C to D, and then thereafter from D to E, something you can read through yourself. It's the same principle that's being applied. Now, what you'll find, the change that comes about in this lecture compared to the previous lecture, or the stormwater now from B, from the manhole at B to the inlet at C. When we talk of C, we're looking at the middle inlet, or C2. What's on the sketch there? Let me just enlarge that. What's referred to as C2 in that sketch. So, what's the change, or why is it of relevance to you? Is that you'll now learn how to handle multiple catchments. Because now we have more than one catchment. So when we come to the manhole at B, there'll be two catchments. By the time we come to the inlet at C, we'll now be dealing with three catchments. So the pipeline from C to D will have the flow from three different catchments. And we also have a changeover at point C, because point C is a critical point. It's a low point, if you read the notes, and I spoke about that in Monday's lecture. So from point C onwards, the design will have to change, and it'll have to change for a different return period, because it's a critical point. That's quite an involved example for you. Let's look at how we go about it. So in Monday's lecture, we spoke about right up to, we stopped at this point here, the calculations that we had done. So the pipeline from A to B, we selected a suitable pipeline, and if I recall, we eventually arrived at a 300 diameter pipe, or we checked the 300 diameter pipe, and the flow in that is fine. That we have a flow of 157, whereas the capacity of that pipe is greater than that, so we were fine with that. We're now going to look at, we continue now to the inlet at B. So this is the inlet at B, that's the second catchment, and then the manhole at B, right? So there's two separate structures over here. You'll notice that the one is the manhole at B, and one is the inlet at B. So let's just go back to the diagram. Let me just refresh your memory on that. Right, so the inlet at B, that's we're looking at that, was the inlet at B. And when you talk of the manhole at B, then we're looking at that one down there, that I've circled. Right, so the inlet at B basically is the flow that arrives at point B from area 2. Right, so it's this a singular catchment again at point B. So it's just there's only the only flow that arrives there at this B, if you want to call it B1. Right? It has a subscript, a small little subscript there. Let me say now, just it has a subscript, so it's B1, and we're going to now determine the flow that arrives there for catchment 2. Area 2. Now we have the area here, 0.5 hectares. We have the length of that catchment area. And again, there is no clear defined water course. So then the assumption is that we'll have overland flow, and all that overland flow arrives at this point, B1 level. That's a pretty straight, very similar to what we've done in Monday's calcs. So you'll see straightforward calculation again, and something you should be able to follow quite easily. That you got this time the area, it's a much smaller area. You got the length of the catchment, uh, and then the fall of it. Again, this information is given to you. Uh, it's actually just given in the solution. I haven't come across it in the actual question itself. When you look at this diagram, you're not really given indication of what the levels at B1 are, or what the levels at B, for example, or the upper reaches of the catchment. So there are no contours or anything on this drawing. So you'll have to just take it, whatever they've done in the solution. Obviously, if you had only the sketch as you see it like this here, you would not be able to work it out. That's some information that it's missing from this particular worked example, but it's given in the solution. So one would presume that this is just a design sketch that they've marked up of the catchment, but they have a contour map or something, and they measured. They've got those levels out from a contour map. Right? So let's look at that. So we're coming back to. Sorry, let's just turn it. Right, so we take it for now that this information can be determined from some point, the 5 meter fall. Once you know that, you know what the fall is or the average grade. You'll notice this time you come up with the average slope of the catchment of 4.1%, which is greater than the 3%. So obviously it's going to change this runoff coefficient for your Kirby formula. Um, and then you just substitute into the Kirby formula. You got the length, you got that, and then you just work it out, and you get the concentration time of 18.3 minutes. That runoff coefficient of 0.4 from the Kirby formula, we're working with 4.1%. Let me just recap that with you. I'll just take you back to that Kirby formula. Just bear with me. I've got to page through all of the stuff here. I haven't actually memorized the page numbers, so you just have to bear with me while I find that sector. That's the Kirby formula, and you can see that the runoff coefficients again for that. Okay, we've got the slope. So I was in error there. It's related to the runoff coefficient. Okay, it's not at the slope of the catchment. When we're working off the runoff coefficient for the catchment area, then we'll need that slope over there, 4.1%. But over here, it's, in the Durban area, we can assume that we have moderate grass cover in that catchment area. So that's where that runoff coefficient of 0.4 has come from. So that was an error from my side, where it's mentioned it's related to the slope. The slope will be for the C coefficient, the general coefficient, and this is where you'll find that we'll be using this value of 0.11 for that particular catchment over here, because 4% lies between 3 and 10% there. Right, so that was just an error from my side. Let's get back to that particular 27, 28, okay, consider at point A. So we're looking at this inlet at B. Right, so the 0.4, that's related to the type of terrain that we have, and we're saying moderate grass cover there. Right, so the concentration time, plain straightforward, 18.3 minutes at that point. It's greater now. The design code mentions that the concentration time should be at least 15 minutes. That's the bare minimum that we'd use. So you would, because it takes at least 15 minutes from the time that for that flow, or that's the experience, past experience in Etigwini. For most catchments, almost all the catchments, it would take at least 15 minutes. So that's why we would work with that 15 minutes over here. Remember, from the time, why that 15 minutes also is got to do with when it starts raining immediately, you do not get flow immediately. It does take a while to build up that flow. Right? Initially, you get the ground would be slightly more permeable. It would be, you can assume it to be dry. So there'll be some absorption into the ground, so you won't get flow immediately. And then also the ground itself would be rough, right? It's not perfectly smooth. So you get indentations in the ground. So also for the first few minutes, the water will be filling in those indentations. So you don't actually get flow. What you're getting is wetting of the ground initially. So it takes time for a while to get that wetting of the ground. And thereafter, after a short time, then only you will get actual flow occurring, where you start beginning to get the sheet flow or flow in a water course there. That's the reason why we have a minimum value for 15 minutes of air. Right, so once we've got the concentration time, then to estimate the runoff, and this is where I mentioned to you about that slope value. Just now, I pointed out to the table that for the 4.1%, we used a value of 3.011. Uh, then, for depending on the type of vegetation that we have and the type of soil, the permeability of the soil and the type of vegetation in that area that we have, we will then read off the appropriate values for, and one we will let's just check up like the CP and the CR point 0.2 and 0.25 in the table. So let's go back up to the table. I just want to show you that 0.2 and 0.25 that we used. Okay, now. Okay, so the point two that we have from it, so that's the permeability for most soils. So we're just assuming it's a typical soil in the Durban area. So that's where we had that point two from there. And okay, the initial I mentioned about the 0.11, that was the value for that one. And then for in Durban, we generally will be working with a grassland area. So that's why we have 0.25 there. And for each of these values, we're working with 100% of the catchment is grassland, 100% of the catchment is semi-permeable, and 100% of the catchment we're assuming is the slope is between 3 and 10%. Right, so in the yellow column, we'll have 100% for each of those, and the other other cells will be zero over there. So that's how we work out that. It's 28. I'm just changing the page number. So right, so that's how we came up with the catchment runoff coefficient for area 2. So that's why we've called it C2, and we get a general value of 0.56. Again, we still assume we're working with a 5-year. These calcs are done to a 5-year storm, although the most recent guidelines say 3 years the storm return period. So, but all of these calcs are done for 1 in 5 year. So we then need to work out the rainfall intensity. First, we need the point rainfall. The rainfall intensity comes to 110 millimeter per hour, and that's done by using the concentration time of 18.3 minutes. So that's the time, 18.3 minutes. We have done that, the concentration time for that catchment area. And we need the point rainfall in terms of millimeters, and that we will then go back to that same table, the Excel spreadsheet that I showed you in the last lecture, and you should be familiar with that by now, the same latitude and longitude that we have. And we can then read it off for a 5-year storm. Right? So this time for 18.3, so we won't have a column for 18.3. We'll then have to interpolate it between the 15-minute and 30 minutes. So we interpolate between those two times, and that's how that value of 410 millimeter per hour was arrived at in these calculations. Right? If you don't know what's happening or how to do it, go back to the Monday's lecture and you see I have explained that in detail, where I opened that Excel spreadsheet and I showed you how to look up the correct values for that 15-minute and 30-minute storm for the relevant latitude and longitude, and also to find the correct return period and things like that in the table. Right, so then plain straightforward, you can then work out what's the flow, 0.35 cubic meters per second. You now just substitute into that into this equation here. All of these, the return period value, it's still 1 in 5 years. So we'll use the appropriate return period for that. I think it was 0.55, if I recall. Yes, that's 0.55 in that formula there. So plain simple substitution, and we then can calculate the flow. Beyond After this, it's similar to your sewer design. You can check it for your sewer design. You can even take out those tables there. You given the grade of the pipeline between B1 and B2, and you can then select a suitable pipe. Start off with the 300 millimeter pipe because you're not under a road. So we'll work with the 300 minimum. If you're in a road servitude, you would then work with 375. Right? And then you can then going to decide for that for the flow that we worked out. 3.5, we need a flow of 0.035 cumex. The capacity of that 300 millimeter pipe at a 1 in 20 slope would be 0.392, which is greater than that. So we find, and the velocity of flow in the selected pipe is negligible. What they mean here, it's the pipe is so short, so they're not really considering the concentration time. It will just take a few seconds, right? Maybe 3 or 4 or 5 seconds for the water to flow from this inlet to manhole B. So that's why that's not really being considered. In the calculations I've done, I have actually worked that out. Let me just show that to you. So I did my, just bear with me while I open that file. Just to show you, okay, I'm just going to see, consider the pipeline AB, that was the first pipeline. Concentration at time at B. So you can see I've done the calculations also. You might find it easier to follow these calculations. The time of concentration, the same 23 minutes for the, okay, that's when the flow arrives at point B. Then B1, this is what we were considering now. So the same calculations. And why you might find it easy, because you see I've written down where all those values were arrived at from. Right, so how you got those C values, how you arrived at that C2 values. And that's the 18 minutes, right, the concentration time. And then the time it takes for the flow from from this inlet at B to the manhole at B. Right, those two, that's short pipeline over there. So that's the. This is now going on, moving. You can see that's how that 110 value was arrived, the interpolation between those two values. So you have to find those two values in the spreadsheet like that. So you've got that, and that's how the 110 was arrived at. And then I just want to show for that pipeline at B, then to work out the actual, so just bear with me. That pipeline B1. So this is the selection of the pipeline that's in the Itegwini calcs. It's just done in 2 lines or 3 lines. So here you have the detailed calculations showing you how it's all done. And what I want to get to is the concentration time. Right? So if you look at it, the concentration time at B. Okay, there's the time. The flow. This is what I was looking for. The information. The time it takes for the flow from that inlet at B1 to the manhole at B is only 5.4 seconds. So because it's such a short distance, so that's why it was stated there as negligible. Right? It's not that the velocity itself is negligible. I think the wording is not right. What they meant is that the actual time that it would take to flow there would be negligible. The velocity, we can check it for that particular pipe. This is similar to your design that you've done in sewer reticulation. The full bore velocity was 3.6 meters per second. And we then, if you check the actual velocity in that pipeline, I just want to, where was it here? The actual velocity there, that's the actual velocity, was this 2.757 meters per second. So quite a significant velocity, not something that's just like negligible or something. It's yeah, just something I wanted to bring your attention to in this calculation. So what they mean is that the time for the flow is negligible in that particular pipeline. Right, so now the next part is for manhole B, and this is where this is in this lecture. This is what I was alerting you to, that for manhole B. Okay, so this is page 30. I just want to go back. I think it was page 27. The diagram. Yeah. Now we're now looking at the total flow at manhole B, because we want to design the pipeline from B to C, like that, right? So that's the pipe. We want to design that pipeline from B to C. So we need the total flow arriving at this manhole B. Now, at this point, this manhole B, you now have the flow from two catchments arriving at this place. So you have the flow from catchment A1 and catchment 2. So two separate catchments, the flow will arrive at point B, and you now see how do we handle that. Uh, what runoff coefficient are you now going to use, right, for these? In this situation like this, what runoff? What will be your concentration time also for this particular situation? So that's what makes it interesting. And now it's the first time that you're actually handling such a case like that. It's not so. It's nothing difficult to it. There's no. Uh, just explain it to you. So there's just a few changes, a few adjustments you have to make to the calculation. So for manhole B, we now have area 1 and area 2 contributing. Right? So the total area, you now, for the total catchment area, so what we need to do is we will now work out, okay, in our rational formula, the total area will be, we'll have to take the sum of the areas for area 1 and area 2. Right, so that will be the change from the previous. Not really a bigger change, but not a major change, but it'll obviously have to be the total area of the catchment. But then if we're working with the total area now in our rational formula, right, so we'll now be working with that value in our rational formula, then we need the C value for this particular catchment. Right. So in our rational formula, we now need the C for the total. We need the C total value for that over there. It can't be the C for either catchment 1 or catchment 2. So we have to go back and rework out our runoff coefficient for this total catchment, right, for area 1 plus area 2. So to do that, and also the concentration time that we're going to need, we'll need the concentration time for both of those areas. So how long does it take? What's the longest time it takes for the water to reach at that manhole B? Right. So that's what we will have to look at. So we'll have to compare how long does it take from catchment 1 for the water to arrive at the point at manhole B? How long does it take from catchment 2? How long does it take for the water to arrive at point B? And then we'll have to take the longer of those two values. That will be the larger of those two concentration times, and that will be our concentration time. So you see here they talk about the longest travel time, right, to manhole B, and that gives you get the value of 23 minutes. Right? And this 23 minutes is the flow that it's taking from catchment 1 to arrive at this point. Because for catchment 2, okay, let me just delete all the clutter here just to make it clearer for you. For catchment 2, so let's bear with me while I just delete it. Right, so for catchment 2, we had a concentration time of 18.3 minutes, plus that if you're going to be technically correct at manual B, to that 18.3 minutes, you need to add 5 seconds. So that's 5.4 seconds. So it's not really going to change this. It won't even change this last decimal significantly. Right, so that's why it's just being less. So for catchment 2, it's 18.3 seconds. Whereas for catchment 1, if we come back here, you'll recall that the time that it takes for that water to flow in the pipe from point A to point B, we added all of that up, and we have a value of 23 minutes. So it's the larger of these two values. That's what we will have to choose. So it takes longer for the flow from the furthest point in catchment A to arrive at point B. Then it takes flow from the furthest point in catchment 2 to arrive at point B. So that's where we got the 23 minutes. So we now got to compare that. We got to look at our different catchments and determine what's the longest concentration time that we have, right? Or the longest time of travel. So that was we get the 23 minutes. That's where the 23 minutes came from. We then need the C total, the runoff coefficient in our rational formula. So we now need a new value. But now we have two catchments with different properties. You'll notice that, okay, we use the same permeability, we used the same vegetation value, but the slopes were different. Right? So the runoff coefficient is going to change. So how do we allow for that? We will then take a weighted average for those two coefficients. We worked out what the coefficient for the first catchment was, C1. We worked out what the coefficient for the second catchment was. And now you can see, if you look at the formula that's being used here for the runoff coefficient, for the total one, this is the C total value. Right? So the formula for the total one, that's where you're seeing it over here. And what in effect this is a weighted average. They call it mean representative value. We take the coefficient of the first catchment and multiply it by the area of the first catchment, and we add it to the product of the coefficient for the second catchment by the area of the second catchment, and then we're dividing it by the total area. Right, so total area. So in effect, what we're saying here is C, the total value. We're taking C1, A1, the area of one letter, plus C2 area 2 and dividing it by A1 plus A2. That, excuse me, I'm writing with a mouse, so I'm really struggling to do that. A2 letter. So that's a plus sign. There should be. I haven't written that correctly. It's not the product of it. It's the sum of that A1 plus A2. This excuse my writing because of the mouse. So that's what this is what we did. This in maths. So you'll come across it You'll come across it reasonably often in civil engineering, where we take the weighted average value. So this is what it's referring to, is a weighted average. I know when you do foundation engineering, you come across this weighted average when you get to your honors level and you do foundation engineering. We'll use this weighted average again. And in other places also in civil engineering, you come across this. So this is what we do. So this is the change that's what's different now. When you got multiple catchments, and each catchment has its own coefficient, but to work out the combined coefficient for each one, we take a weighted average letter. So we take a weighted average coefficient, and that's what's being done over here. So once that's done, so then we now need to, we have the C value, we then need to work out the I, the intensity, and for that we need the point rainfall and the concentration time. The concentration time we said for this combined catchment was 23 minutes. So 23 minutes is the combined time. We're still working with that 5-year storm. And we then get to go back and interpolate for that 5-year storm for that, and we will then now arrive at a value of 93.1 millimeter for that for this particular value over here. Right. So when you the actual point rainfall, again I can show that to you, the calcs that we have. So we had the 93.1. If I come back here, let's go back to this. The concentration time was B in pipeline B. Just bear with me. This is what we're doing here. Sorry, I'm just going to see from that value. We took the weighted. Okay, that's the total. That's the total flow. We substituted in that far. I substituted in that far. This is. You'll see that I've written it out in more detail in the steps. Easier for you to follow. I'm now looking for the I value, the IB that we interpolated. Okay, this is the value. That's the time of it. So it's the same. This is how we arrived at that 96.7 for that particular the rainfall intensity. Right, the concentration time. I worked at the actual ones. I worked to more decimals, so that's why you have this. Uh, in the Iteguini count, they just say 23 minutes. I've added for that extra 5 seconds of flow in the pipeline, and you can see it's the same value because it's the same storm and the same interval that we're working with over here, right? So 29.8 and 38.9, like in the previous value. So 96.7 millimeter of rain. That's the point rainfall. And you then divide this 96.7 by the concentration time of 23 minutes. right? And you got to be careful when you do the division also because it's in millimeter per hour. Your concentration time is in minutes, so obviously you got to convert that the minutes to hours, and substitute and then put it in the numerator. So in the denominator, and then work out that value of millimeter per hour. Right? So just be careful with your units when you're working to work out this rainfall intensity. You got to convert the concentration time to hours. So that's how so the point rainfall was 96.7, and then to work out the intensity, you will then divide that by the concentration time, and then you'll arrive at the correct answer for the intensity for this particular to substitute in this equation over here. But so then let me go back to the calculation here. Uh, that's the I 93.1 that you have over here that you substitute in that formula, and then you can then work out what the total flow. And well, you again the surveyed grade. This is this given to you in the questions. You would have to know. You need more information to determine this. This is just provided for you in this drawing. Maybe from the road design or from some other design, you would have had you will pick up the slope of the pipe, or sometime it's you will have to decide on a suitable grade for that particular pipeline. In practice, you would have to actually decide on the grade of those pipelines because you're designing those pipelines, and you can choose a suitable grade so that you will get it to work. This time, because you're going under a road, the minimum pipe diameter would have to be 375. Let's just go back to the diagram. I just want to show you 27. You can see there's a road there. So the pipe is going to cross under a road. So you need a minimum pipe diameter of 375. But if you under a road reserve, so that's when you need the minimum 375 diameter. So let's go back to those calculations. Come back here. 375, that's what we said there. And after this, it's pretty straightforward. You can now use the same tables that I showed you for sewer reticulation design, and you can then check the suitability of that pipe. You'll come up with a value that at that grade of 1 in 80, a 375 millimeter pipe, concrete pipe, with the suitable manning coefficient and things like that, will have a capacity of 0.23 cumex, whereas our actual flow is only 0.181, so it's more than enough, and that's how we would select the 375 pipe would be adequate for that over here. But, there's quite a bit of calculations missing from here. You'd have to go through like what we've done in our sewer calculations and double check the actual velocity, check the depth of flow in those pipes and things like that, and just make sure everything works out well there. Then we come to uh, the crux of it all here in this particular design. Consider the inlet C. Right now, inlet C, that's where we now will pick up the catchment from, or where we get the flow from catchment 3. And because that's a low point design, it's the low point in the drawing, so it will be a critical point, right, in the design. And I just want to alert you to this, that this is something that this is an ETGWINI requirement, and it's a perfectly valid and makes sense. It's like when you're doing wind design, when you're designing for a particular element, then the intensity is more at that particular point. So you need to, for a critical element, you would up the return period, or you would up the loading at that particular point or something like that. So it's the same thing over here, that you have a critical point in your design, and you would then design it for a more severe storm than for the lesser storm, because uh, you may have and what is a critical point? Right? So, for example, where you may have damage to infrastructure, or you may have damage to private property, or depending on the type of intersection, the road, sometimes the way one road comes downhill and it intersects 90 degrees with another road, and you have properties in front of it. So there are various categories that would define a critical point. I just want to take you back. Let me just go back and show you what they call a critical point. Not 29, so 26. I just want to take you in the notes, in this ETB notes, the way they mention what's a critical point, right? This one in terms of methodology, it's not over here. In this, but you can see under the general methodology, part of it is to identify the position of critical points. You can see there, right? And so, but they've defined what a critical point is. So this take you through that section of the notes to alert you to it. Partial kind of verbs, inlets, bends, losses. So just bear with me. I just want to show you the relevant something that you should actually read over and be aware of. Minimum cover. We have spoken about this in partially in the design. I have covered that about that something. Just bear with me. Bear with me. It's somewhere here. Diameter and fall intensity. This is where, okay, right. So if you look under the section 3, that's the 3.1. Dimension is measure of critical points in the design. Right? And for a critical storm, that's what they mentioned, that you've got to design for a 1 in 10-year storm, at once in 10-year storm. So irrespective if you're designing for a 1 in 3-year or 1 in 5-year return period, at the critical point, you will design it for a 1 in 10-year storm. And the reason behind it is the likelihood of heavy economic losses or social inconvenience. And where are these places that you should identify, or where will these critical points occur? They have been listed over here, these three categories. So at a low point where you can get ponding, and then you'll get overflow, and then you'll get erosion of the bank, right, by flooding or whatever, or low-lying, or you can get flooding of low-lying property. Right, so that's the one area that you would be concerned about. And commonly, you'll read in the press, or sometimes there's a storm, just a normal storm, and then you get flooding, and it's usually a design error with regard to this, for this first point over here. Right? It's also one of the reasons why one should not build in a floodplain. Right? Or you got to normally every municipality will, for all the water causes in within the municipality, they will have the flood lines, 1 in 10-year flood lines, 1 in 50-year flood lines, 1 in 100-year flood lines. Right? And they have regulations that one should not build within the floodline. Right? So that's just by the way. But okay, so this is a critical point, the three types. The second one is at the intersection of a steep road with a flat road. Where water flowing down the steep road. What they refer to, again, this is actually, in essence, if this situation does occur, it's more likely a town planning error that has occurred if this situation arises. But when the township design is being done, it should have been avoided. And what it refers to is where you have a road, for example, you have a road like this, and you have an intersection, a T intersection like this. Now, this is normal. This is not a design error. This is something you have to do. You design all the time. Where you have this kind of an intersection with a road. That's a normal. But what it's referring to is where let me call this a road A, right? And I'll call this a road B, like this, road B. Sorry, just excuse my mouse. And you have properties along here like this. So you have properties along this road like this at this particular point like that. There's properties like that, for example. And road A is a steep road. So it might be on a hill, for example. So this is this road A is coming down a hill, right? So road A is coming down a hill, and this is flat over here. This is a flat. So you got water that's collecting from the hill. It will have a large catchment area because this might have other roads that feed into it like that have other roads. As this road goes up like that, and remember it's going up a hill like that, and it's picking up the flow from other areas and other roads. So you got a large volume of water coming down the road because generally we use our roads also as stormwater channels as such we use them for transmitting the stormwater into the municipal stormwater systems. So you have a large volume of water coming down, and it's coming down very fast. It'll have a high velocity because this is downhill. Right. So remember, this is on a hill, and it will then shoot across. Yeah, it's gonna. You can put a catch pit or whatever, something. You can try and have stormwater. Things to try and catch the stormwater at that point. But because of the velocity of it, it's so fast, it just shoots across and then it floods these properties here, or you're going to get damage in these properties over here because the water will just shoot right across and come there. If I were to draw a section that what it's referring to is you have a road. This is the flat road. So if I'm trying looking at this road here like that, and you then have the other road coming in, for example, steep like that over there, and we then have properties across or buildings or whatever, something like that. And that's what you can see, water coming at high speed. And you can put what you want over here. You can have catch pits or whatever to try and this thing to try and take that water. But because of the velocity, some of it will go into the to your stormwater facilities that you provided, but most of it is just going to shoot across into that property and cause flooding in that property like that. Right. So if you situations are like this, if you do have situations like that, then that's what this is telling you. You need to design for a 1 in 10 year storm. Uh, but ideally, this should not be like that. When it came in the town planning, they should have actually re-looked at the way that that intersection is shown. One would not normally have an intersection like that. If you have one load to run one a very steep road joining up into a very flat road like that. Right. So this is the situation. Then the third one is at the site of an important drainage structure. Right. So this is like the way the confluence of a road with a major stream like that. Uh, so where you have now you have this convergence of a few structures, stormwater convergence into a major structure, and that's you now means you're now uh, going into a major stormwater system where you link up with your major stormwater system. That remember we differentiated at the beginning when I started with stormwater. I explained to you about you get the minor stormwater system and the major stormwater system. The major one is the municipal one, and that's where you're going into your main water courses or rivers or things like that. So that's where you got these important drainage structures. Then you need to do that. So getting back to our design here. We are sitting in case A. Here. That's a critical point because we have a low point in the road at that point. So that's why we have to then design it for a 1 in 10 year storm. The short of the long story here is that we have a low point. It's a critical point. We will design it for a 10-year storm at this point of view. So let's get back to that our design here. Right. So coming back to this point here, so that was a critical point. So we now have to design a 10-year storm, and now this is going to change things, because up to this point we're working with a 5-year storm. So you'll see how it does it. So you now have to adjust for that. We have the catchment 3 or area 3. This is the data for it. It's pretty straightforward. And like we've previously done, what we've done for the previous catchments. So you find this, again, this substitute for that again, or we're working with overland flow. So we use the Kirby formula, and it's the slope part of it. The slope has changed. We now have a 12% slope, so it's steeper. So we just substitute into the formula there. The rest of the coefficients are still the same. And we then arrive at we now got a concentration time of 17.3 minutes at point C. Uh, so, right, so that's fine. We have 17.3 minutes there. We then need to estimate the runoff coefficient for this particular for catchment 3, and we do that similarly to how we have done for catchment 2. We just get the appropriate values for these. The CP and the CR values will still be the same as the previous catchments. It's the CS, the one for the slope, because now we at 12%, so we just need of the appropriate value for that, and we will then get a runoff coefficient of 0.65. We will obviously again take a weighted average for the final runoff coefficient, and you'll see that for the flow at C, in the total flow at C, that's where we under the same like what and for the then work out what's the intensity of the storm and whatever like that. The area for the third catchment, the concentration time for the third catchment, we have there the runoff coefficient, which we've just calculated for that particular catchment. I just noted they got 0.6 here, but they have 0.65 there. That's fine. And then because it's a critical point, you'll now notice the change. It's been determined for the 10-year storm. So we will go back to that Excel spreadsheet, and then you will look up again. And similarly, you'll find the point rainfall and then divide the point rainfall by that 17.3 minutes per second, and you would then get the intensity 143 millimeter per hour. For that, so you mentions it, use a 10-year intensity, and you can then work out what that total flow arriving at that point C, right? So arriving at you have 0.62 meter cube per second. Right, so that's for arriving at that catchment from catchment. So this is the data for catchment C. At inlet and the point in consideration is that inlet C there. We now want to select a suitable pipe between that pipe between C and D. Right, so we now at this point C. So let me just go back here. 27. Right, so we've now worked out the total flow arriving for that. We've sized the pipe AB. We've sized the pipe BC. Now we want to look at the pipeline from C to D. Like that, right? So from C to D. So we now need the flows from catchment from this area 3, area 2, and area 1. And we also need to look at how long it takes, what's the longest time for the flow to arrive at this point C. Right, we have three catchments, and we need to look at what's the longest time it would take for that at that point over there. So I think it was page 31. That was on page 30. Okay, so for to determine the flow at at C. So this is now inside the catchment itself. That's from C to D. We're going to now design the pipeline from C to D, and we want the total flow that will occur in that pipeline C to D. So the area, the total area, we now have to take the area of three catchments, catchment 1, catchment 2, catchment 3. So that's fairly straightforward. We just sum that up. Then the concentration time that we need for the design of this pipeline CD. Now, the one is for the third catchment we worked out, and that was 17.3 minutes. Right? So that's one value that we have here. We then got to look at from the previous the pipe from B to C, right? What's the concentration time for that flow when it arrives at that point C? Okay, so let me just delete all this clutter here so we'll have a comparison when we come back. So it'll be easier to pick that up. So remove all the extra writing over there. Right, so we're going to then compare it against that value. We'll have another value and compare it against this value, and then we'll get the longer one. So the concentration time at C for that pipeline, right? So we now, okay, let me just go back here, 27, page 27. We're going to look at, from this point in the catchment area. So from that point, or for that matter, from that point here, how long does it take for that flow to arrive at this point C over here? Right, so how long is it going to take for that flow to arrive at that point over there? So that's what we want, is the longest time for that. Now we already know that the time it takes for this flow to arrive at B is less than the time it takes for the flow from this A to arrive at this point B. Right? So we need the concentration. So we can ignore the area 2-1 because we know area 1 takes longer. There's a longer time for the arrival of that one. So we will now check for that area 1. How long does it take for that flow to arrive at that point C? Right? And that will be the larger of our concentration time. So we then let me go back here to the calculations. So that's what we're doing here. So you can see for area 1, right, the concentration time, which we had worked that out. we then have from the time it takes uh, from from that in the pipe from point A to point B, and then the time it takes in the pipe from point B to point C. So we add all of that up, and we end up with a value of 23.5 minutes. Okay, I just want to delete the extra thing. And so we will then compare this value with the time it takes for the flow from catchment 3 to arrive at that point C. So we have 23.5 minutes versus the 17.3. So the larger time is that 23.5 minutes. So that's the larger time that we have there. Now, the mean or the weighted average of the runoff coefficient at point C must be determined, and it will now be for the weighted average for the three catchment areas. The last time we had for two catchments that we had, the two catchment was A1 and A2. This time we got for A3, so similar kind of formula like what we used before. Right. This time in the denominator we'll have area 1 plus area 2 plus area 3, and on the numerator you got the product of each runoff coefficient times its particular area. So you'll have three terms on the top and those three summation of three terms in the bottom line. And we then arrive at the runoff coefficient of C equals to, so the C total this time will be C is equal to 0.57. The intensity of the rainfall um, for this particular, we now notice here that we looking up for the 1 in 10-year storm. Right? Notice that 1 in 10-year storm, not the 1 in 5-year storm, because we now have changed over to design from at point C. We're designing it for the 1 in 10-year storm. So the 10-year storm, we will now have to re-look up what's our intensity. We go back to that Excel spreadsheet, and again, you're going to interpolate between the 15 minute and 30 minutes, but you're going to interpolate for a time of 23.5 minutes. Right? 23 because that's our concentration time. So when you interpolate for that 1 in 10-year storm from the Excel spreadsheet for that 23.5 minutes, that's how you arrive at this 120.8 millimeter per hour for your intensity, the rainfall intensity that you have there. And so then you can now substitute into this value and you get the a total flow of 0.482, and this is the flow that you need to design the pipeline between C and D. You're given the grade of it. This grade you'd obviously have to check it. You need the contours for that area, and you determine a suitable grade for the pipeline for that. But you're not given that information, so we're just taking it as a given grade over here. So you can then check now for a 1 in 75 slope. You now got to select a suitable pipe. You can see immediately the last time we had a 1 in 80 slope and we used a 375 pipe, and our flow was much smaller than that, but we were quite close to that value. So obviously the 375 pipe is not going to work. You then will select a suitable pipe, and you can see a 535 diameter concrete pipe. This to arrive at this value, you would need to use the notes that I've given you for in the sewer reticulation. You have that nomograph, and based on that nomograph, you can then select a suitable pipe to try out. So you try out the 535 pipe, and then you can do all the calculations and check it, and you'll see that yeah, a 535 millimeter concrete pipe at the 1 in 75 grade has a capacity of a full bore capacity of 0.592 liters per second. Right, you're going to use your Manning equation, whereas we want 482 to 0.482 to flow, so it's more than adequate, and then it'll be fine. You can then check the velocity of flow, and then you can also work out the time it takes for the flow in that within that length of ponds. You got the velocity. You can also work out how long it will take for the flow to occur in that pipe from C to D, like that. Right? So that's where they get the half a minute. Right? So not half a minute, 0.3, a third of a minute. That's how long it takes for the flow in that pipe. Right? So we have a C, manual C there, and then we have catch put C, and then we have man D, and then you got the pipe that's flowing across like that. So that's the time it takes for the flow in that pipe from C, point C to point D, 0.3 minutes. Like that. At 0.3 minutes will mean that's about a third, so it's about 20 seconds or something like that, 20 to 20 something seconds. That's what it would be. Okay, so that brings us to the flow from point C to D. So this part here was the critical that I wanted to alert you for was this particular section, the flow from point in the pipeline from point C to point D, because you notice that we changed over to a 10-year storm. But now you'll notice also that this intensity here is being applied to, this is for the 10-year storm, and it's being applied even in catchment A, in the catchment 1, catchment 2, and catchment 3. Right? Because the area, the total area is for those three catchments, and so that's where we're applying it to those three, to all of those catchments, and we're now working with the 10-year storm. The concentration time is not affected, if you look at it, when you're determining the concentration time in this. Let me go back here to page 27 time, page 27. The concentration time in that Kirby formula that you have here, that's not affected by that 5-year storm, 1 in 5-year storm, or 1 in 10-year storm. Let's just go back to that formula here. I just want to show you the runoff coefficients. No, not that. Bear with me, please. I won't be long. Oh, I've passed it. That's this particular one. Right, so you notice that when we worked out those concentration times for the catchment 1 and catchment 2, or area 1 and area 2, when we worked out this value, it's not affected by the return period for the stormwater return period. It's just affected by the roughness value for the surface and the slope of that particular catchment. That's what comes in these formulas. So that's why we did not go back and recalculate the concentration time for catchment 1 and catchment 2 for that 1 in 10-year return period. It would still be whatever, irrespective of the return period of the storm, it would still stay the same. Right, so it's not affected by the return period of the storm. Similar argument would apply for if you were working with a natural water course also. It's not affected by the return period of that storm. So that's why we didn't have to recalculate that. Interestingly, in this discussion, let me go back to that page 27. So let's bear with me. Interestingly, what is affected by the return period was the time it would take for the actual time it would take for the flow between A and B, and between B and C, the flow in the pipeline. And because the quantity of flow that you're going to have at point A, that is influenced by the return period. Right? So, but we're still using that same, um, and if the quantity of flow changes, then the velocity actual velocity also would change, and then the concentration time, the time it takes for flow between A and B and C would change slightly. But because these pipelines are relatively short and the time it takes, we're looking at just a few seconds. So it's not going to make any significant contribution, right, or change in our calculations, because it would just be a fraction, maybe a few seconds, right? So a fraction of a minute in terms of the time difference between 1 in the a 5-year storm and a 1 in 10-year storm to the concentration time for the flow from point A to arrive at point C, rather. So this is something to bear in mind when we're doing these calculations, and that was not taken into account in these calculations. Is ignored because it will be significant in terms. It's not going to affect these values here. As you see, we've used just to come back to these calculations. Sorry, I'm jumped the gun a bit here. We for C, okay, that value is correct. We got no problem with that. But in this particular one, we looked at the concentration times for this when we arrived 3 minutes for that. 3 minutes was actually worked out for part of it is for a 1 in 5-year storm. but it's not going to make a significant difference for the 1 in 10-year storm. So it's fine. We still work with that, and we arrive at the correct. I'm just sorry, I was at the wrong one. This is what I'm referring to with the concentration time. These values that we have here, this 0.5 minutes and 0.5 that the part of that's for the catch for the flow in the pipe, the flow in those pipes over there. We had a very small this thing. So maybe you might end up with maybe 23.6 or so maybe you might end up with 23.4 there because you'll have more flow. So you might have again that's depends on or the depth of flow that you have over there. It become too complicated to consider that. So, technically speaking, there is 100% correct. You can actually go back and readjust the flow times that you have two values there. Come at almost the same value. 3 and 5. Okay, so taking the pipeline CD, we've got a manhole D to the outlet at E. So let's just go back on this diagram. 27. The last stage of it, we've now designed the pipeline from C to D. We've chosen that 35 millimeter diameter pipe, and now you need to design the pipe from point D to point E. So the pipeline from that point over there, and then there's another small bit of pipe from E to F like that over there. Right. But you notice that for D there is no inlet, so it's the same flow that we used, exactly the same flow that we in the pipeline CD. That's the same flow in pipeline, but this you have a longer pipe now, and the grade might be different. So that might affect. So that's the only change at that point. So let's go back to those calculations. Uh, uh, it's the same area as previously as for inlet C. The runoff coefficient is still the same. There's no additional area. There's no additional catchment area. The intensity the same as we had like previously. Okay, now so the intensity will change. It seems that I think there was a slight break in my internet connectivity. Okay, you haven't really missed much. I don't think I've missed much. Okay, I was talking about the flow. So for the pipeline from D to E, the area would still be the same. The runoff coefficient would still be the same. The intensity value would change slightly because the concentration time would change slightly. Because you now have the concentration time. Let me just come here. Sorry. The concentration time. I just want to go back to the page 27. The diagram here. The concentration time would include the time it takes for the flow from C to D. So it will be just a little bit more than the concentration time at point C. So that will affect the intensity because the concentration time is longer. So the intensity would then reduce slightly compared to the previous value. Right, so let's go back here, and we see that's being done in these calculations over here. So that's why the slight adjustment over there, you can see slightly because we're now working with a time of 23.8 minutes as compared to previously. We had a concentration time of still 23.5. You can see it's made hardly any difference from 23.5 minutes. That was the 23.5 minutes on the top there to 23.8 minutes now because of the time it takes for the flow in that pipe over there. So it reduced the value very slightly, 119.8 as compared to previously 120.8. That's a very slight reduction in the intensity because of the longer time, concentration time. And then you work out the same, very similar value like previously. very similar slope. Like last we had the one in 75, we one in 80. The selected pipe because of the slightly flatter pipe, 600 diameter pipe. So obviously for that the one in uh, 75 does not work for the previous, so that's why they went for the one in 80. You got a flatter pipe, so they have to change the pipe diameter. Always note that for stormwater, we never go into you always increase the pipe size. You never decrease the pipe size. Even if the slope would get steeper, you would not go down to a smaller pipe diameter. That's a you can read through all of this calcs. And you'd follow it over there. And then the last bit of again for that E to F, the design of that pipeline again, and just to check it again. Similar procedure like what we've done previously. There are no additional catchment areas coming into that, so that's why that's a similar procedure to that. I'm not going to go through that last bit. You can read. I'll leave it to you to read through that by yourself. Sorry, oh, no, I'm wrong. For uh, at point E, there is an additional. You got area for 4, but you already. I've shown you for at point B and at point C. When you have this additional catchment, it is the same principle like what we've done at point C would apply at point E, and for the pipeline between E and F, and you'll design that over there. That's a very comprehensive example for stormwater design. Uh, Please read through this solution. There's a lot to it that goes to it and takes a lot of understanding. And you'll only really get to grips with it when you do the calculations yourself. Take out a pen and paper and work through it by yourself and do all these calculations. Right? You will also need that spreadsheet. It is on Moodle. You can download the the Excel spreadsheet for the eThekwini rainfall data. You will need all of that data to do these calculations over here. Well, in a test or exam situation, also, I would expect you to be able to read off those values. Uh, you would be expected to find the correct spreadsheet, look up the relevant latitude, longitude, and be able to read off the point rainfall from those spreadsheets. Okay, so that brings an end to this section on stormwater. Now, this was just a design example, uh, but I also expect you, as part of this module, to read through uh, the, the design information that's given to you. So, for example, the method of stormwater reticulation design, the general methodology, you should be familiar with that. And also with regard to that section 3, that we this whole section 3, that the design of a minus system. Right. So all of this with regard to the we've spoken about this. You should be fully aware of that. This minimum diameters, the minimum velocities that you expected, you got the minimum velocities, the materials, about anchor blocks, about curved alignments, things like that. So I would expect you to be familiar with all this information that's given here in this section 3 for this particular module, right, for the stormwater design. Any questions with that? That'll end the section on stormwater design. Any queries, anybody? Okay, if there's no further queries, I can end the recording. Stop the recording.